In this video I will talk about interrupts because on this robot, the robot that I'm programming in this video series, I have a few cases where I'm going to be relying on interrupts. And also this video series wouldn't be much of a video series about embedded systems unless I at least said something about interrupts, because interrupts is such a fundamental mechanism when it comes to or when you work on low-level hardware on a microcontroller, for example. More specifically in this video, I will first of all I'm going to talk about why we need interrupts and how they work. I will try to keep my explanation pretty brief because there are already so many other resources on the internet explaining how interrupts work, so I don't feel the need to go into it in depth in this video. Instead, I want to more focus on showing some code examples and also implementing some better handling for interrupts in my in this project that I'm covering in this video series. So after I explained why we need interrupts and how they work, I want to show a code example. So first I'm just going to show an isolated code example, and I'm actually going to have ChatGPT generate this code example because I want to show how surprisingly well ChatGPT is at generating examples even in this context of embedded systems for this specific microcontroller. And once that code example works, I'm going to move on to my actual project code. And in my project code, I'm going to add a couple of functions to make it easier to register new interrupts to my GPIO pins. Because normally when you add an interrupt, you will have to write to the registers of the microcontroller directly, which is a bit cumbersome. And as I did in the video where I show you how I program GPIO pins, if you haven't watched that, go check it out. I like to write some C code or an abstraction layer that makes it just more pleasant for me as a programmer to work with the IO pins. So I'm going to do something similar for registering interrupts. And finally, I will take the opportunity to also increase the clock speed of my microcontroller in this video, because currently the clock speed is running at 1 megahertz, and I want to increase it to 16 megahertz, which is the maximum for this microcontroller. Not because I really need to do it, since 1 megahertz is enough for the application or for this project, because the clock speed is not the limiting factor when it comes to the code that I will be running on this robot. But I'm just doing mostly because I can, and if I'm going to change it, it's better if I change it now before I start working on the rest of the drivers, because some of the peripherals depend on the main clock, because they derive their own clock from the main clock. So for example, I2C and timer peripheral. Okay, so let's now talk a bit about why we need interrupts and how they work. To understand interrupts, I think it's best to first imagine a world without interrupts, which is arguably a world not worth living. In this world, we will have our microcontroller, and the processor on this microcontroller is going to be executing its instructions one after the other. So it's going to have a bunch of instructions inside its flash memory, which it's going to be executing one after the other. So the PC is going to be pointing to one of the instructions, and then it's going to execute the next one, and the next one, and the next one. It's executing the instructions that we have told it to execute by writing our C code and compiling the C code into machine code and then flashing it onto the flash memory of this microcontroller. If you want to know more about how the memory of a microcontroller works, you should check out my previous video where I go into depth about that. And having the microcontroller execute instructions exactly as we have told it to is going to work well as long as the microcontroller doesn't have to react to any kind of events or anything happening inside its environment. In other words, it's going to work perfectly well as long as the microcontroller is in an environment that is perfectly deterministic and that we can, when we write our code, already predict when everything is going to happen. But of course, in practice, this is normally never going to be the case, because for the microcontroller to be useful in most cases, it's going to have to react to events that we can't fully predict when we are writing our code. So, for example, let's say we have our microcontroller and maybe it's connected to a button. And when the user presses this button, we want the microcontroller to react to this button press and to do something. So maybe the microcontroller is also connected to a display. And maybe this display is showing some kind of graphical user interface. And when the user presses the button, we need the user interface to be updated. So maybe the button press causes another menu item to be selected. And since we don't know when the user is going to press the button, we can't just write a predetermined program that is going to update the user interface after a given amount of time. Because maybe the user presses the button after 10 seconds or 12 seconds or 3,333 milliseconds or whatever. We can't know. And as such, for this to work, we need the microcontroller to have some sort of mechanism to detect when the press happens and then to react to it. And if we stay in the world without interrupt for a little longer, the way we can solve this is by having the CPU periodically check if a button press has happened. So let's say that the pins on the microcontroller is connected to some sort of hardware block. So I'm just going to redraw this here. And this hardware block handles this hardware block detects when the logic level or the voltage level of the IO pin changes. And when it does, it's going to write to some sort of register. So for example, let's say that when the button is pressed, the voltage level of the first pin changes, and then this hardware block here writes to the register and sets the first bit of this register to 1. And the CPU can then access this register to figure out whether the button has been pressed or not. This means that we can have the CPU figure out if a button press has happened by inserting an instruction that reads this register here. So read register. And then we can have an if statement to check whether the first bit in this register is set to 1. And if it is, we know that the button has been pressed, and then we can react accordingly to, in this case, update the menu on our user interface. So for this to work, when the CPU or the microcontroller is executing, we would have to check this register periodically. So we will have our microcontroller executing its normal program, and then periodically, from time to time, we will have it check this register to see if a button press has happened. And this approach, where we detect if an external event has happened by periodically checking for a condition to be met, is what we refer to as polling. And while polling can be a viable solution to this problem in certain cases, polling does come with some obvious disadvantages. First of all, since the CPU is going to periodically check the register to notice if something has happened, it's going to have to spend extra CPU cycles doing that. And as long as nothing has happened, it's essentially just going to be wasting those CPU cycles. And ideally, we want our microcontroller to always be spending its CPU cycles on doing useful work. And secondly, the time it takes for the microcontroller to react to the external event is entirely going to depend on how often we check the register. That is, the latency is going to vary depending on how often we check the register. And where we want a very low latency, we will have to check the register more often, but that also means that we're going to be wasting more CPU cycles. A third big disadvantage with the polling is that it entirely relies on the microcontroller being up and running. And this means that the microcontroller can't be in a low power mode where we clock down the microcontroller or simply turn it off or put it inside a standby mode, which is often common these days in battery powered devices when most of the time the device is going to be in some sort of standby mode, and it's only going to be waking up when we press a button or it needs to collect some data or whatever it's doing. And if we are going to be reacting to events through the means of polling, that means the microcontroller has to be up and running all the time, and that's going to consume current and going to reduce the battery life of these devices. So these are some of the disadvantages with polling. You can probably come up with more disadvantages, but it's safe to say that polling is not a very good approach to solving the problem of having the microcontroller or the CPU be reacting to external events. And this is where interrupts come in to make the handling of these events more efficient. And at a high level, an interrupt is basically a signal sent to the CPU that tells the CPU that something just happened. And when the CPU receives this signal, it's going to stop what it's currently doing. That is, it's going to stop executing its normal program to jump into its handling for the event that just happened. And when it's done handling the event that just happened, it's going to go back and continue executing where it was interrupted. So from the program point of view, it's going to be like nothing happened. The only difference is basically that there is going to be an additional delay between two instructions of the main program. Of course, this is a very simplified explanation of what an interrupt is. So if we take a closer look at how this is actually implemented. First of all, interrupts are mostly implemented in hardware, and this means that the exact implementation is going to vary between processors and microcontrollers and so on. But in general, how it's going to be implemented is that the CPU is going to have some hardware lines connected to it, so-called interrupt lines. And usually there's going to be some dedicated circuitry or a dedicated hardware block for handling the interrupts. And this hardware block is usually referred to as the interrupt controller. And this interrupt controller is in turn connected to all of the other hardware blocks that may cause an interrupt. So for example, we may have a UART peripheral, which may cause an interrupt, for example, if it has received a byte or if it, for example, has finished sending a byte. And similarly, I2C may have an interrupt to notify when its transmission is done. And then we may also have an interrupt coming from the I/O ports. And this interrupt controller is usually going to have some registers associated with it. So it may, for example, have a register for enabling and disabling interrupts, which we sometimes call masking an interrupt. And you will see later in the code example that I'm going to show that we have to explicitly enable the interrupt for the event coming from one of the peripherals to actually trigger an interrupt. So if we continue with the example that I showed before with the button press, we can take a look at what steps are taken from when the button is pressed until the interrupt has been handled. So let's say that the button is connected to this port 1 here. So when this button is pressed, it's going to assert the line connected to the interrupt controller. And if this specific interrupt has been enabled, the interrupt controller is going to forward this interrupt to the CPU by asserting a line connected to the CPU. And when the CPU notices an interrupt, it's going to finish executing its current instruction. And then it's going to save the state of the program. And by saving state, I mean that the CPU has a bunch of register that it uses to keep track of the current state of the program. So it has a register for keeping track of the current program counter, which is a register that points to the current instruction the CPU is executing. And it also has a register to keep track of the stack pointer, which is the register that points to the top of the stack. And then it's going to have some status registers and some general registers. And when it prepares for handling an interrupt, it's going to save some of these registers. Exactly which register it's going to save is going to depend on the CPU. But in general, it's going to have to save the program counter, the stack pointer, and some status register, and maybe some general registers as well. But for this example, let's just assume that it only saves the PC, SP, and the status register. And it's going to save these registers to the stack. So let's just sketch up a memory map here to make it easier to understand. And saving the state is going to be done in hardware. So this fifth step here, some of that may actually be done in parallel to the fourth step. So done in parallel as the CPU finish executing its current instruction. And then when it has saved its state, it's going to retrieve the address to the function that is dedicated for handling the particular event that has just happened. And this function is usually referred to as ISR, the interrupt service routine. And this is a function that we programmers have to explicitly define inside the code, which I'm going to show you in the code example later on. The ISR function is going to be located somewhere inside the program memory. And as with any other function, it's going to have an address. But also as with any other function, it's not going to have a fixed address. That address can end up anywhere in our program code. And this means that the CPU must be a bit flexible in how it retrieves this address to the ISR function. And the way that's usually implemented is that there is going to be a dedicated table that stores the address to all of the interrupt functions. And we call this table the interrupt vector table. And every type of interrupt is going to have a dedicated location inside this table. So for example, UART is going to have a location dedicated for it. I2C is going to have a dedicated location for it. And port 2 and so on. One of these locations is also going to be dedicated for the ISR that we are looking at in this example. So in this example, if we assume that the ISR has the address 1234, this address will be stored inside this table here. And it's going to be the compiler or the linker that's going to take care of making sure that this ISR or the address to this ISR ends up at this location inside the memory. Because this entire table is going to be part of the flash memory. And you'll see that in the code example that I'm going to show, in order to make sure that the ISR or the address of the ISR ends up in this table, you have to explicitly mark the function to tell the compiler that this function is going to be used for handling the interrupt coming from port 1. Okay, so there is going to be a table that contains the address to this ISR. And this table, or the addresses to the individual elements in this table, are going to be fixed. So the addresses here, let's just assume for simplicity's sake that they start at 001 and counts up from there. So for example, the address to the memory location that contains the address to this ISR is, let's say that's stored at address 3. This address 3 is going to be fixed. And when the interrupt controller handles one of these specific interrupts here, besides just asserting the line to the CPU, it's also going to make sure that there is a register that gets filled with the address to this memory location here. Or usually it's going to be the offset from the start address of the interrupt vector table. So the CPU is going to read this offset register and it's going to add it to the start address of the interrupt table. And that's going to give this address. And then it's going to take the value from this address, which is in this example 1234, the address to this interrupt service routine. And it's going to load the program counter with this address. And when it has done that, the program counter is pointing to the first instruction of the interrupt service routine, which means that it has started executing the interrupt service routine. And the first thing that happens when the interrupt service routine is executing is that there may be some additional instruction that the compiler adds for us here to save some additional registers that are used inside the interrupt service routine. And exactly which registers it saves here is going to depend on what the interrupt function is doing. That is, if it's keeping track of a lot of local variables, it's going to be using more CPU registers and going to have to save more registers. And if it's a very simple interrupt service routine, it may not save any additional registers at all. But the saving of these additional registers is going to be completely invisible to the programmer, because that's taken care of the C compiler. But if you, for example, for some reason implement your interrupt service routine in assembly, then you need to make sure that you save the registers that you make use of inside your interrupt service routine. And then once these registers are saved, it executes the code inside the interrupt service routine. And then once it reaches the end of the interrupt service routine, it's going to restore the state. And that means that first the additional registers saved by the ISR are going to be restored. And then any status registers, PC counter and stack pointer are going to be restored. And then once that's restored, it's going to continue executing where it was interrupted. And one thing to note here is that all of the steps between 2 until 7 is done entirely in hardware, and step 8 to 11 is done in software. That means that from step 2 to 7, when the CPU is preparing for executing the interrupt handler, it doesn't actually spend any CPU cycles doing it, because that's done by hardware in parallel. Note the flow I'm explaining here is a very rough explanation of what happens, because exactly how this is implemented and the exact flow is going to be very implementation specific, so it's going to depend on the particular CPU and microcontroller and so on. And there's also going to be more complexity to consider on a modern CPU, because you are going to have to consider like the priority between interrupts when multiple interrupts happen at the same time, and a lot of other details that I don't want to get into here. But this is broadly what happens when an interrupt occurs. So if we just shortly compare interrupts to the polling that I showed before, there are some obvious advantages. First of all, since interrupt doesn't require the CPU to periodically execute extra instructions to notice if an event has occurred, it doesn't waste any CPU cycles. It's also going to react to the event quickly, so the interrupt latency is going to be low. And it's also possible for the CPU to be in a low power mode where it's not executing any instructions, and then to just wake up when an interrupt occurs. So it improves on all of the problems that I mentioned about polling before. So given all of these advantages with interrupts, we should also ask ourselves if there are any disadvantages with them. And I think the biggest disadvantage with interrupts is the complexity they introduce. I mean, having all of these events that may get handled at any point in our program execution can easily end up introducing a lot of unexpected behavior in our code. And it can sometimes be hard to debug why something happens, because we can't step through our code as we usually do when interrupts occur. So let's now see if I can use ChatGPT to give me a simple example that enables the interrupt on the first pin of this microcontroller. So now it has given me a code example here that I'm going to paste into my IDE, and it has also explained exactly what this code is doing. Pretty awesome. Essentially what it's doing is first it's disabling the watchdog timer, and then it enables interrupt on the first pin of port 1, and it sets the pin to interrupt on the falling edge, so when the pin goes from high to low, and then it clears the interrupt flag just in case. And finally it enables global interrupts. So as you can see here, to enable the interrupt for a pin, it's not only enough to enable the interrupt for this specific pin, you also have to enable interrupts globally for interrupts to even work at all. And then we have our interrupt handler up here, and it's marked specifically as an interrupt handler for the port 1 vector, and this means that it's going to end up inside, or the address to this function is going to end up inside the table, the interrupt vector table, as I explained before. Okay, now I'm just going to add some additional code here so it's easier to see that it works when I run it on my microcontroller. I've only added a simple variable that I increment inside the interrupt handler, and then I keep on looping inside the main function until the count reaches 100. And I'm marking this as volatile here, and here it's really important to mark it as volatile since it's changed inside the interrupt function. Otherwise the compiler may think that it can just optimize this count variable away because it's not changed inside the context of this function. Then I'm just going to plug in my launchpad and run this. Sometimes it doesn't work on the first try for some reason. And then I can put a breakpoint inside the interrupt function and run the code. So when I'm not doing anything, the interrupt shouldn't trigger. But if I connect a jumper wire between positive, like in this case 3.3 voltage, and connect it to the first pins, well, you probably don't want to connect it like this because there is no resistance in between, but I'm going to do this anyway now. So when I connect it, the pin goes high, and then when I disconnect it, it goes low again. And since it It's set up to trigger on the falling edge. It's going to trigger when I disconnect the jumper wire again. And as you can see, it has triggered now. Oh, and yes, it's going to keep on triggering here, because on the MSP430, you have to actually explicitly clear the interrupt after you're done inside the ISR. Otherwise, the interrupt flag is going to remain active and keep on triggering the interrupt. So at the end of the interrupt, I actually have to clear the interrupt for this to work. I can run this again. So if I connect the first pin, pull it high. Now it triggered immediately here, since when I connect the line, it may, like, the voltage may wiggle a little, and that may cause an interrupt, even though I haven't actually disconnected the wire yet. But if I resume, it no longer keeps on triggering the interrupt, but if I disconnected it now, it should trigger the interrupt, and it does. And then I can have a look inside the memory browser to see where the to see the memory location of the interrupt vector table. And I don't remember where the address to this table starts, so but since I have ChatGPT here, I can just ask ChatGPT. So the interrupt vector table starts at address FFC0, and ChatGPT is also giving me a lot of additional information here. But if I search for this address inside the memory browser, I should see the address to this interrupt service routine. So I can even hover this. So this, the address to this function is this value here. But it seems that I think the memory browser feature of the IDE doesn't work when you use the GCC compiler, perhaps. So let me just see if this works on the TI compiler instead. So I'm going to ask ChatGPT to make this code compilable with the TI compiler instead. So now it's just going to change how the interrupt service routine is marked, because it's marked in a different way when you use the TI compiler instead of the GCC compiler. Otherwise, the code is going to be mostly the same, though it for some reason put the count variable inside the interrupt service routine here. That's not going to work, so we'll have to change that. The code should work the same now. It's just that I've compiled it with a different compiler. So we can just double check. Yeah, it still triggers the interrupt. So the address to the interrupt service routine is located at this address now. And if I search for the start address of the interrupt vector table again, I hope to see, with the TI compiler, I can actually inspect this area of the memory that contains the interrupt vector table. And if I check the address of my interrupt function here, it's C1BA. And I can see that that's stored at this address here, FFE4. So the address to the interrupt service routine is stored inside the interrupt vector table, as we expect. So when the interrupt happens, the CPU is going to take what's stored at this address and load it into the PC register. Now I would also like to show you the disassembly of the interrupt service routine, just to see if this interrupt service routine saves any additional registers at the start of the function. But in this case, since the interrupt service routine here is very simple, it immediately just increments this variable here, and it doesn't save any additional registers. Then we clear the interrupt flag, and at the end we call the RETI operation, and this is the instruction that's going to restore the PC, SP and the status registers, and maybe some additional registers depending on what registers the CPU saved when it entered this interrupt service routine. But if I make this function a little bit more complex, maybe have a couple of local variables here, and just for demonstration's sake, I'm just going to make them volatile to ensure that the compiler doesn't optimize them away. And then I will just add them to my count variable. With these additional variables now, if we look inside the disassembly view, you can see that before we increment the count variable, there is some additional code that has been generated by the compiler that saves, in this case, register 12 to the stack. And then at the end of the function, when we are done, it's going to pop and restore register 12. And this means that depending on how complex your interrupt function is, depending on like how many variables it's using, the compiler is going to make sure that additional code gets generated at the beginning and at the end of the function to save the state of the registers. So at the beginning it saves the registers it's going to make use of to the stack, and then at the end it restores the registers by popping the values from the stack. What I would like to do now is jump into my normal project code and add some better interrupt registering and interrupt handling for the IO pins on my microcontroller. So I'm basically going to add some additional functions inside my IO driver. And I'm doing this to make it easier for me to register new interrupts on the IO pins. And these are the functions I will have in my interface. So the first function is going to configure an interrupt for one of the IO pins, the IO pins that's passed as the first argument. And the next argument decides if the interrupt should trigger when the pin goes from low to high or high to low. On the MSP430, it's not possible to configure it to trigger on both edges. You can only trigger at one edge at a time. And then finally, I will have this function take the interrupt service routine as an argument, and I've actually created a type def here just to allow me, since usually when you write a function pointer it's quite ugly in C and not very readable, so if I type def it like this I can just write ISR function, which I find much easier to read. This will essentially let me, in the file that I'm calling this IO configure interrupt, I will be able to have define my own interrupt function like this. And then I can just call IO configure interrupt, pass the first arguments, and then I can just pass the name to my ISR function like this. I also need to add this trigger enum at the top of this file, next to the other enums. Then I can jump into the implementation file. And I'm going to access the interrupt related registers in the same way as I access the rest of the IO registers. And if you want to know more about how I do this, you should check out my previous video, how I program GPIOs. The first array holds the registers for the interrupt flags, and as I showed before, the interrupt flag is set every time an interrupt happens, and I have to explicitly clear it inside the code after I've handled the interrupt. And then there is the registers for enabling the interrupt, and these must be set for the interrupt to even trigger. And finally the registers for selecting whether the pin should trigger on rising or falling edge. And on the MSP430, even though there are 3 ports on the version I have on my robot, only the first 2 ports are interrupt capable, so you can't get interrupts on port 3. And that's why the IO interrupt port count, this define, I'm going to set this to 2. And then I'm going to create a table to hold the individual interrupt service routine that are associated to each pin. And since there are 8 pins per port, there are going to be 8 possible interrupt service routines. And at the beginning, none of these are going to be assigned, so all of them are going to be set to null. And then I also need to add a new enum for the ports, since I don't have that yet. And as I mentioned before, the difference between the microcontroller on my robot and the one on the development board, the launchpad, is that the robot has 3 ports and the launchpad only has 2 ports. But interrupt wise there is really no difference, since only the first 2 ports are interrupt capable. And then I can go ahead and implement the functions that I declared in my header. So these functions. Let's go to the bottom of this file, starting with IO configure interrupt. And I'm going to have this function called to other functions. So first of all, it's going to set the interrupt trigger, and then it's going to register the interrupt service routine. And then I can go ahead and implement these functions. And these should be static since I'm only accessing them inside this function. And for this function, I'm going to implement that in a very similar way to my other IO functions here. So I can basically just copy one of these functions and then replace some of the variables inside it. So switching on the trigger rising, IO trigger falling. One thing to note here is that something that's mentioned in the datasheet is that when you configure the trigger of a pin, that may actually trigger an interrupt itself. So just to avoid any unintended behavior here, I'm going to, before I configure the trigger, I'm going to disable the interrupt for this pin. And after I've configured the trigger, I'm also going to make sure I clear the interrupt flag. Because another detail to be aware of here is that even if you disable the interrupt, that's not going to prevent the interrupt flag from being set if this pin triggers an interrupt. And since this is not obvious, I'm also going to add a comment above this function. Set. Then I also need to define the IO clear interrupt function. And this is also only going to be called inside this function, so I'm setting that to static, so it's only available inside this compilation unit. And this is just going to be a one-liner. Okay, and then I'm going to implement the IO register ISR function, which is also going to be static. And I'm going to begin this function with an assert that asserts if an ISR has already been set for this particular pin, so that I get an error if I accidentally call IO register ISR on the same pin multiple times. And if it's null, it means it's not set, and then I just set it to the ISR function that was passed. And then I can go ahead and implement the opposite function of IO configure interrupt, which is IO deconfigure interrupt. I'm probably never going to call this function inside my project, but I'm just adding it here for completion's sake. And that's first of all going to unregister the ISR. And I'm also going to have this disable the interrupt. And then I also have to add a function for unregistering an ISR. And for this function I can just copy the implementation of the register ISR and remove the assert and just set this to null. And this function is only going to be called inside this function, so I can also mark this as inline to avoid the function call overhead, which should save me a couple of bytes of flash memory. And then I can implement the function for enabling and disabling an interrupt, and those are just going to be one-liners. Next, I'm going to write the code that's necessary to ensure that when the interrupt occurs on one of the pins, that the right ISR function gets called. Because as the code is now, there is no one that's going to call the ISR function. And just as I showed in the example from the IDE, I need to add a function that's attributed like this. So that's what I'm going to do now. One important thing to note is that there is only one ISR per port. So all of the pins of a port, the 8 pins of a port, are going to share the same ISR. And we have to explicitly check the individual interrupt flags to see which interrupt that actually triggered the ISR. So I'm actually only going to have 2 of these functions here, one per port, port 1 and port 2, like that. And just to make this code a little bit more readable, I'm going to put this in my own define instead. A define call interrupt function. And this is going to let me short this to interrupt function port 1 vector instead. And I think that's a bit more readable. And I'm also going to name the function a bit differently. So when I pin on one of the ports, on either port triggers, if it's port 2, it's going to trigger this function, and if it's port 1, it's going to trigger this function. And now inside these functions, I have to check which pin actually triggered the interrupt. And to keep things as short as I possibly can and to waste as little flash space as possible, I'm going to have a for loop looping over the individual pins. And the same in the other function. And then I'm going to define this IO ISR function. And in this function, I'm first going to check if this was the pin that triggered the interrupt. So I'm going to check the interrupt flag. And if this was the pin that triggered the interrupt, I'm also going to see if there is any ISR function registered to this particular pin. Oh, I think I made a mistake in the function up here. This should be IO pin index. Same goes for this. And if this is not null, it means that there is an ISR function registered to this interrupt. And then I'm simply going to call this ISR function like that. And once I've handled the interrupt, I also must make sure that I clear the interrupt. Can add an additional comment here. So once again, when an interrupt triggers on one of the pins of port 1, this function is going to get called, because the compiler and linker has made sure that this function is part of the interrupt vector table. And when this function gets called, I'm going to loop over each individual pin to see which pin it was that triggered the interrupt. And when I find the pin that triggered the interrupt, I will end up inside this if statement. And then I'm going to check if I registered an interrupt service routine for this particular pin. And if I have, I'm going to call that interrupt service routine. And once I'm done, I'm going to clear the interrupt. And then to test to make sure that all of this works, I'm going to add a simple test function inside the file. And the way I'm going to implement this test function is that I'm going to configure two pins, one pin on port 1 and one pin on port 2 as input pins with the pull-up resistor. And I will be configuring the second pin of port 1 because I'm going to use the first pin to blink an LED. And then I will configure the interrupt for these individual pins. And I'm going to have both of them trigger on falling edge. And then I'm going to define the interrupt service routines up here. And I'm going to have the first interrupt service routine turn on the LED and the second one to turn off the LED. So if I build this code now, it's probably not going to compile because I most likely made a mistake. Yes, missed a semicolon. So I will just have to fix my mistakes. It should be pin index and port interrupt edge. So I'm not actually using that. So what am I? This should be named regs instead. Like that. If I build again. Yeah, so since I'm using null, I also have to include std standard definition. Now it built. So now if I flash this onto this launchpad, I should be able to pull the two pins low in order to turn the LED on and off. So let's see if that works. It's not working because the LED is blinking, and this means that I trigger an insert for some reason. So let me just debug why that is. The reason it was not working was because I had made several mistakes. First of all, I was trying to build for the wrong target. So I built for the robot instead of the launchpad. And that's why I got an assert, because I have an assert inside io.c, inside io init, where I check whether I built for the right target. So I was triggering this interrupt here. And the second mistake I made was that I hadn't actually enabled the interrupt here. And I also need to make sure that I stay in this function, so I have a while loop at the end here, so that I don't end up triggering this assert instead. And finally, I also need to enable the interrupts globally. And there's already a function provided for this, and that's the enable interrupts. So that enables the interrupts globally. Because it's not enough to just enable the individual interrupts, the interrupts also has to be enabled globally. So if I build and flash this code now, so at boot the LED is not going to be on, but if I pull the second pin of port 1 down, the LED turns on. And then if I pull the first pin of port 2, the LEDs should turn off. And it does. And then I can do it again. Turns on. And turns off. So that works. That is, when I pull the pin down, or the 2 pins down, it triggers these 2 interrupts here. So the first interrupt function turns the LED on, and the second interrupt function turns the LED off. This is a very simple test function, so it's not actually testing all of the code that I've just written, so there may be some additional bugs here. But I'm going to take the risk here and assume that everything works now. And then I can go ahead and commit the changes that I just made. But first I need to create a local branch, and then run static analysis on the code. Format the code. I should also run the script that builds all of the test functions. That works. Then I can go ahead and add my changes and commit. And then I can push it to GitHub. Open a pull request and make sure that it passes CI, and it did. So I go ahead and merge the pull request. Bam. The last thing I'm going to do in this video is to increase the clock speed of the microcontroller from the default 1 MHz to 60 MHz. And the microcontroller I'm using in this project is actually aimed at low power application, and as such it has many different clocks, and you can configure them in different ways to trade off performance for power consumption. But for my application I'm just going to configure the microcontroller to run at its maximum clock speed, because I don't really care how much current or power the microcontroller consumes in my robot, because even when it's clocking at its maximum rate, the amount of power it consumes is going to be negligible compared to how much my motors consume and the other sensors connected to this board. And there are a lot of details to go into when it comes to the clocks on this microcontroller. And as always, how these clocks on the microcontroller is configured is going to be explained inside the datasheet. So if we just have a quick look inside the datasheet, there is an overview of the clock module on this microcontroller. And the clocks that I'm going to configure now is going to be the subsystem clock as well as the main system clock. And the main system clock is used to clock the CPU and also some peripherals. And the subsystem clock is only used for clocking some of the peripherals. And I'm going to have both of these clocks derive their clock from the digitally controlled oscillator, which is an oscillator that you can configure to run at different clock speeds. And by default it's running at 1 MHz, and I'm going to increase it to 16 MHz. There is also another clock up here called the auxiliary clock, but I'm not going to configure that in this video, but I will use this clock later on in this video series. Another thing to be aware of with this microcontroller is that you are going to have the option to connect an external oscillator. And that is if you have an application that requires an oscillator that is more precise than the one that's provided internally. But I'm just going to rely on the internal oscillator. So what I'm going to do now is I'm going to configure the digitally controlled oscillator. I'm going to configure that to 16 megahertz. And this configurable oscillator also have a reference oscillator. And this is an internal oscillator, and that oscillator is also configurable, and it also has to be configured to 16 megahertz. So that's also something I'm going to do in the code. And then I'm going to make sure that the main system clock derives its clock from the DCO, and also the same for the subsystem clock. So both of these are also going to run at 16 megahertz. And the way you configure the clocks is going to be similar to how you configure anything else on the microcontroller. There are a couple of registers you need to write to. And first of all, I'm going to make sure that the define I use for busy waiting is going to work the same after I change the clock rate to 60 megahertz. I'm going to add another define here. So when the CPU runs at 16 megahertz, it's going to be clocking 16,000 times per millisecond. And that means that if I want to busy wait for 1 millisecond, I need to busy wait for 16,000 clock cycles. And then inside MCU init, I've already prepared a function that configures the clock. So I have a function called init clocks. And the first thing I do in this function is to sanity check the calibration value. Because when this microcontroller is manufactured, there are going to be some variations between the units. So all of the units are not going to run at the same clock speed by default, because they are going to have some differences in their physical properties. So as part of the manufacturing, TI runs calibration, and it stores the specific calibration values for the particular unit inside memory. And the first thing I do here is just to sanity check that there are actually calibration values inside these memory locations. If they for some reason have been erased, I'm going to assert here. And then I configure the main clock, or the internal oscillator, this reference clock here, that's used as a reference for the DCO to run at 60 megahertz. This essentially takes the calibration value and writes that to this register. And next I configure the DCO to also run at 16 megahertz. And similarly, there is a different configuration value to configure this. And then I must also ensure that the main clock and the subsystem clock actually derives their clock from the DCO. And to configure that, you should write to this register, but this register is already configured to do this by default, so I don't actually have to explicitly write to this register. So I'm just leaving a comment here to make that more clear. Then I call this function inside the function where I do the rest of the initialization. So immediately after I've stopped the watchdog. And to test that this still works, I can just run the test function that asserts, because the assert blinks the LED every 250 milliseconds, and it should blink at the same rate as before if everything works. And it looks like it does. And I can actually, just to double check, I can go into the assert function and modify it to blink every second instead. Yeah, and now it blinks every second. So the configuration works. But I'm going to change this back to 250 again. Then I can commit this code as well. But first I have to, well, I'm going to stash these changes, and then I'm going to fetch the latest main, check out main, and then check out a new branch. So that's going to be fix increase clock speed 16 megahertz. The stash. Now I have to run all of these again. Oops. No. Then I can add my changes, commit. Create a pull request. CI, I rebase and merge. So that's it for this video. See you in the next one.